All right, so new unit, Unit 5. We only have 5, 6, and 7 for this semester, so we're well into finishing up for what's going to happen before Christmas. And we're looking at atomic structure and periodicity. So the first thing I want to talk about a little bit is color. Why are things colored? How are things colored? Any things here? I'm going to walk through so people can hear. It says, talk loud, Moss. Okay, light gets reflected back, but why? Wavelengths of what, though? Like photons. Why are photons being reflected or absorbed? I heard someone say. Yeah, but by what? What are these colors absorbed by? You're speaking where I don't. I want details. More details. What about the electrons? Are you eating while you're talking? Swallow your granola bar and then answer me. Oh, he's still chewing. Sorry. He's still chewing. Hold on.
The electron, like cloud, absorbs some of the light and reflects some of it like back.
Okay, the electron cloud. Good. How?
Different charges, I guess, of the light.
Close. The electrons, when the electrons are actually exposed to light, are going to absorb different quantum or different packets of this energy. And when they do, they'll jump up and then they'll fall down. And we'll talk about why that gives us different colors when we get to that. So it is based on the electron movement. So when you're talking about light reflecting and all this different stuff, it is based strictly on the fact that the electrons are jumping and falling because of their exposure to full visible spectrum of light. So if it were really dark, and I'll address this in a minute, but I just want you to think about this. Don't actually answer it yet. But if it were truly dark, like truly no light, is there color? So if you had a shirt on and you went down five miles down into the earth and there was absolutely no light, is your shirt still colored? Think about it. Think about it. We're going to address that in a second. All right. So let's go and just talk about light first and the properties of light and things you need to know. This is very much stuff that you're going to cover in greater detail in physics. For those of you who have taken physics, you're going to be at a big advantage at this point. But on the AP equation sheet, there's some equations that you're going to have, and some that one specific one that I do want you to memorize because you got to learn it for physics anyway. But it's all based around these properties of light: wavelength, frequency, and speed of light, as well as something called Planck's constant. So we know light travels in waves, and in our world, electron and wave, because of that duality, is pretty much the same thing. I know it's weird to think of an electron being a wave, but that's one of those crazy things that you'll learn when you get to quantum chemistry in college. But if we have a wave, what is the wavelength? Two peaks, peak to peak distance, or top. Anywhere in the wave cycle that's the same, like from there to there, that would be one wavelength. And it's measured in a unit of length. We can measure it in meters, which is going to be what we want due to the fact that the speed of light is measured in meters per second. But oftentimes, they're going to give us a more useful unit, and often we need to know how to convert from nanometers. Nanometers are used because wavelength of light is teeny, so we want a number that's going to make things a little bit easier. There are 1 times 10 to the 9th nanometers in 1 meter. Think nano 9, nano 9, nano 9. Okay? What is frequency of a wave? Fast, sort of. Miles can read, yes, the number of waves that can pass per second. So we have a point in space. How many wavelengths pass that point per second? The units on this freaks people out. It's per second, 1 over seconds. This is also known in the radio world as hertz. When you tune into a particular frequency on your car radio, that's what you're tuning into, the frequency. So 98.7 is a frequency. One thing I didn't mention were these little symbols. You've got to know, that's called lambda. You don't need to know it's called lambda, but when you see that, I want you to be thinking wavelength. It looks like this. Okay? This is nu. These are all Greek letters. It's a V. Either in type, it's usually just an italicized V, but if you're writing it, it tends to have a little tail. That's frequency. Okay? Speed of light you need to know. In physics, they have you just say 3e8, which is fine, whatever. But on your AP sheet, I just need you to realize it's going to be written 2.998 times 10 to the 8th. I say anything you do on the AP exam, use exactly what's on that sheet that's given to you because it'll be apt to match the rubric answer. So the closest you can get to the rubric answer, the less chance there is for graders to make mistakes. Okay? So this is how fast light travels per second. And then there's something called Planck's constant. I believe you guys derive this in physics. I'm not sure. But it is a constant that we use in calculation of energy. This will be given to you on the sheet, so don't memorize it. 6.626 times 10 to the negative 34th joule seconds. You have some equations that you'll be given. This equation is given to you on the AP equation sheet along with energy is equal to Planck's constant times frequency. You don't need to memorize these. I find one very, very useful. You're going to have to learn it in physics. I use this equation more than any equation, and it's just the combination of the first two. If you do want to use this, unfortunately, you're going to have to memorize it because it's not on the AP sheet. I think it's worth it because it takes a lot of problems that you have to use two equations for and makes it just use one. Do y'all see where it comes from? E equals H. It takes this frequency, makes this equation solve for frequency, and do C over lambda, and just puts it in there. Okay? So that might be a good one to have in your back pocket. So let's do some math with this stuff and see how y'all take to it, and then we'll talk about the theory behind light. So here are some waves. If you notice, these all have different wavelengths. So let's talk about the relationship of wavelength to frequency and to energy. If I have this wavelength, let's go extreme. Looking at this wavelength, this has the highest frequency, right? So there's a relationship. High frequency is what in relation to wavelength? Short wavelength. So that's inverse, correct? High frequency, short wavelength. Now imagine if you had a rope and you were trying to make this frequency and you're going like this, faster, faster, faster. How would the energy be compared to like another wave? High. So high frequency, short wavelength, high energy light. You see why that would be high energy? Yeah, maybe, no? Here, opposite's true. If you've got a long wavelength, that is I don't like using short, low frequency, low energy. Okay? Calculate the frequency of light that has a wavelength of 6.7 times 10 to the negative 5th centimeters. So we are looking for frequency and we have wavelength. What equation are we going to use? C equals lambda nu, or C is equal to wavelength times frequency. Okay? So we're going to put in our C. It's 2.998 times 10 to the 8. I'm going to be really a stickler for units this topic. The reason being is you're going to run into tons of situations like this. Our wavelength is 6.7 times 10 to the negative 5th centimeters. What's the problem? We need to be in meters, don't we? So go ahead within the problem and do the conversion, and then it's going to be times frequency. What's the conversion between centimeters and meters? Good. 100 centimeters in 1 meter. Okay, so math people, go ahead and solve quickly. Those calculators out. We're going to go ahead and stick with 2 sig figs here because that's what's given. And what do we get? Can you tell me the first part again? So 4.5 times 10 to the 14th. And what are my units? I'm doing a frequency. Look what cancels. Centimeters went, so we divided meters per second by meters, we get per second, or 1 over seconds left. It's cycles per second. Cycles aren't a unit, okay? You can say hertz, but my only issue with that is it's not a unit per se, and you can't see cancelability when you use it, so I tend to want you to stick to per seconds. That would be what hertz would look like. Calculate the energy of a photon of orange light. This is just of a photon of orange light with a frequency of 5 times 10 to the 14th. A photon is a packet of light. So an electron, they come quantized. They come in a set value, kind of like buying stuff at the store, like an extra value pack or a mini-sized candy bar or a regular candy bar or one of the fun, those big ones, the king size. They come in set values, and electrons respond accordingly. Absorbing a small packet will get it to a certain distance from the nucleus. Okay, and it can't go to a level and a half. It's only going to go to a level in a stepwise fashion. So calculate the energy. We are looking for E. What equation am I going to use? E equals H frequency. So H is your Planck's constant, and that is 6.626 times 10 to the negative 34 joule seconds. And then the frequency is 5.0 times 10 to the 14th per second. All right, seconds cancel, leaving me with joules. And I'm going to go ahead and stick with the number of sig figs given, and that's 2. So what is my 1.3? 3.3 times 10 to the negative 19th joules. Now let's talk about this energy of electrons. Well, actually I'll wait when we get to emission, but the sign of an energy will tell us whether an electron is going up or down, meaning jumping or releasing energy, absorbing to jump or falling to release. We'll talk about that in a minute. Any questions on the equations? Now the next problem banks directly off of this one. This was calculating the energy of a photon of orange light with that frequency. And the next problem, though, calculate the energy of a mole of photons with the same frequency. So what did we just find the energy of? So we found not a photon, the energy of a single photon. So that was kind of like a joule per photon, right? How do I find the energy then of a mole of them? Okay, I'm just gonna probably slap all of you at the same time. Why are you looking at me strange? What if I were to ask you the energy in a dozen of them? What would you do? Hold on, answer my question. If I were to ask you, this is an energy per a photon, how would you find the energy of a dozen photons? Multiply by 12. So how is it any harder? I want the energy of a mole, so what would you do? Multiply by Avogadro's number, exactly. So what was our energy from the last problem? Times 10 to the what? Negative 19 was the joules for one photon, so I'm going to put single photon. So then I know that there are 6.02 times 10 to the 23rd single photons in 1 mole of them, correct? So to 2 sig figs, what would my answer be? .2 times 10 to the 5th? 2.0 times 10 to the 5th joules per mole of photons. So per mole, you know how many things are in a mole. I want y'all to be as familiar with a mole and comfortable with a mole as you are with a dozen, because you have no problem when I said dozen. Okay, but saying the mole freaked you out. You went like blank stares. All right. Calculate the energy of a photon of light. We're looking for energy, and we're given wavelength. Bless you. What do you want to do? You could do both formulas, or you can use the combined one. E equals hc over lambda. So we're calculating the energy. The energy is equal to 6.626 times 10 to the negative 34 joule seconds. What is the speed of light? 2.998 times 10 to the 8th meters per second divided by, okay, what's canceling here? Seconds are going to go. We need joules because of energy, so we need to make sure our wavelength is in meters. What do we have it in? Nanometers. This is going to be a common issue, guys. They rarely give you length in meters. You're going to have to convert it. So nanometers are tiny. So for every 1 meter, how many nanometers do I have? Is that what? 1 times 10 to the 9th. All right, so what is the energy then? .67 times 10 to the negative 19 joules. Not a whole heck of a lot of joules. But again, we're only moving around little bitty electrons. You good with understanding it? Monica, you good? I just see unsure looks. If you don't agree with the number for any reason, you need to tell me, because this is on video and we don't want the wrong answer published to the world, because I'm trusting you guys. All right, last little math problem before we jump into more theory. The energy required to break the oxygen-oxygen bond in O2 is 496 kilojoules per mole. So that kilojoule is busting up how many oxygen bonds? Exactly. We're breaking 6.02 times 10 to the 23rd bonds there. Correct, right? So the question is, calculate the wavelength of light that can break the oxygen-oxygen bond in 1 molecule. So what do we need to do? By dividing by this, what are we actually finding? Kilojoules per 1 molecule, and that's what we want to do. Are kilojoules going to be any useful to us, though? No, so I'm going to go ahead and do a double conversion here. I'm going to go from kilojoules per mole to joules per molecule. So we'll be in joules, because we have to be in joules because of Planck's constant. Okay? So let's do kilojoules to joules first. So for every 1,000 joules, I have 1 kilojoule, right? So my kilojoules go. So now I want to get from moles to just molecules. So for every 1 mole, I have 6.02 times 10 to the 23rd molecules. All right, so this is going to end up being joules per 1 molecule. The energy required to bust 1 bond. 7.49 times 10 to the negative 19. Okay, so, we got a different answer. 8 point what? All right, 8.24 times 10 to the negative 19 joules per molecule. We want the wavelength given, what was this again? We want wavelength given what? What's this? That's the energy. So, how do I get wavelength from energy? We want our little combined equation. So, energy is 8.24 times 10 to the negative 19th joules. And I'm not going to put the per molecule on there because we know that that's the breaking of the 1 molecule. Equals 6.626 times 10 to the negative 34th joule seconds times 2.998 times 10 to the 8 meters per second divided by looking for wavelength. So we want to cross multiply 1 times this divided by 8.24 e negative 19, and that will give us our good old-fashioned wavelength in what unit? Meters. All right, and give me 366. Negative 7. 2.40 times 10 to the negative 7. Does anyone else get that? Yes? Okay. All right, we good? Okay, so now let's talk about all this crazy color business here. This is the electromagnetic spectrum. You don't have to memorize, in this class at least, values associated with wavelengths and color. I do need you to really understand, if I were to give you any two parts of this, which one would be higher energy and which one would be lower energy. So here we have the visible light spectrum right there. And then it's surrounded by other stuff. If you notice, this is going from high energy to low energy. Okay, so you could be given this the other direction. So the visible light then is broken down. What was the way to remember the colors of the rainbow? Where'd you biv? So red, orange, yellow, green, blue, and violet. Okay? Our violet is our highest energy visible light. So it's going to have what kind of wavelength? The shorter wavelength compared to the rest of the spectrum. And what kind of frequency? High frequency. On this end, we got low frequency, long wavelength, low energy. I need you to know what surrounds it. And it kind of makes sense. Red has what's below red in energy is infrared, then microwaves, then your radio waves. What's above violet? Ultraviolet, X-rays, and gamma rays. So you're going to see questions on the AP that'll ask you what has a shorter wavelength, ultraviolet waves or radio waves? Ultraviolet. Those are the types of questions you need to be ready for. Again, I'm not going to ever test you on that. Might I say calculate energy and tell me what color it is or something? Then yeah, then you can calculate energy, or depending upon what they give you, that you might have to find wavelength and apply it to a table of wavelengths. Nothing you can't handle as long as you know how to do your calcs and you know what's left and what's right on this chart. Okay? Now, our first experimentation was done originally with the single electron in good old hydrogen. So that whole Bohr model, which we're about to talk about, and the concentric circles around the nucleus, is basically all a big fat lie. And everything you learn in middle school is a lie. That stuff is only good when we're looking at hydrogen, because hydrogen only has how many electrons? 1 electron. The second we start getting other electrons involved, there's repelling forces and all these different things going on. But what we did get out of the Bohr model, which is really important, was the electron's ability to be excited and go from a ground state to a more excited state. So right now I'm on the ground, right? I'm on a ground state. Here, I'm going to throw this to you. Okay, can you catch? Yeah. All right. So I am now an electron, and now I'm going to be exposed to the entire visible light spectrum. All right? And then I'm going to absorb a quantum of energy based on my characteristics, based on how many electrons are around me. Am I a d electron? Am I a p electron? Am I an s? It all varies. So I'm going to absorb a quantum of light. Peter's going to throw it at me, and I'm absorbing it. And when I absorb it, I'm going to, I shouldn't, my knees are killing me. Why am I doing this? Oh, okay. I'm absorbing it, and now I'm unstable. And for those of you at home, I'm on top of a stool, and I'm in an excited state. Okay? I went from ground state to an excited state, and I have this quantum. I absorbed this and went from a low energy level to a higher energy level. If you look at this picture on top, right up here, That is an absorption spectrum. And you need to be able to tell the difference between an absorption spectrum and an emission spectrum. An absorption spectrum is the full spectrum of light missing pieces that were absorbed. So do you see how those two spectrum, one above and below, kind of complement each other? Okay? So the missing pieces, that's what Peter just threw at me. Okay? That's what I absorbed to get to this higher energy level. Now I'm excited. Do you think I'm very stable? No. So I'm eventually going to fall back to ground state. What happens when I fall to ground state? I lose the same energy I absorbed. Oh, Peter. Peter. I threw the marker at him, and he didn't know it was coming. All right. I lose that, and that is the light that we see, the energy that is emitted in the form of light, and it's a combination of all those colors. All right? So emission is what is emitted when an electron falls. Now let's talk about the thermochemical sign for this. When an electron jumps up, that's the absorption of energy. Just like in thermo, when energy is absorbed, what is the sign on that? Positive. So if I were to do a calc to calculate this energy, it would be positive. When the electron falls, it emits, so it's negative. Now looking at these two pictures, are they absorbing and emitting the same quanta of light? No, so these would be two different color scenarios, two different fingerprints. I need you to be able to tell the difference between an absorption spectrum and an emission spectrum just by looking at it. Emission, everything is missing, but what is getting thrown off by that electron when it falls? So back to that question I asked at the beginning of class, if it's really, 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 really dark, like no source of visible light at all, is there color? No, there's not. It's kind of weird to think about. Has anyone ever been where it's really dark where you can't even see the hand in front of your face? Like down in like a cavern or something? Yeah. There are, what? Well, yeah, it's definitely scary. There is no visible light for the electrons to absorb quantum from and to get the energy. So there is no emission, so there is no color. You've been in low light, right, where colors aren't as vibrant. So not a lot of electrons are capable of doing the transition, so it's less intense. You've kind of seen shades of gray, kind of, if it's dark, the beginnings of those colors. Okay, so let's move on and talk more about hydrogen. So hydrogen in the Bohr model, did lead to this understanding, which is important. It's just way more complex than this because of the shapes of the orbitals and the number of electrons involved. So in the Bohr model, this was originally studied with hydrogen, and it's one electron. You might see these linear pictures of electrons falling from different energy levels. What I do need you to understand, though, is the relationship between the distance of the fall and the energy. So if this is ground state, and I fall from here to here, or I fall from here to here, which of the two transitions, one or two, is going to give off more energy? The larger one. The larger the fall, the more energy absorbed and then emitted. So if it's more energetic, what types of visible light maybe would this be? Visible. You're not visible. So violet, blue, this could be like your blues and violets, right? Where if you just fell like, boop, like that, what visible light might be involved? Your reds, that kind of thing. So you need to understand the bigger the fall, the higher the energy, it's going to correlate to the type of light that could be emitted, either in color or in energy. All right. This is the exact same thing you just saw, but drawn in circles. Okay? Same type of thing. Electrons, and to fall, though, we fall toward the nucleus versus the ground. Okay? We always fall toward the nucleus. So this is a jump up. This is a fall down. This equation right here, I'm going to have you use it because I just think it's really cool, Rydberg. Don't memorize it. You're going to be given, it's going to be given to you in the problems if you need to use them. But what's cool is you can go ahead, knowing the energy level that you're on, figure out the energy associated with the transition. What's also really cool, if you're doing final minus initial, you're going to get the sign associated with the drop or the jump. So if it jumps, what sign should we expect if an electron jumps? Positive. If an electron falls, negative. And if you use it appropriately, you're going to get the right sign. Okay? Again, don't memorize this. Please don't waste your time memorizing it. All right. So you can read more about the good old Rydberg and Bohr in a little bit. But a reminder, this equation I'm about to use is only good for hydrogen. Not good for anything else. It's only good for that one electron. So if we're transitioning from 5 to 2, we're going to plug it in, delta E. It says, what color light? Well, we can go back and try to figure it out based on the energies, but I'm more concerned about the comparison between the two. So I'm using the Rydberg equation. What is the final integer state that we're falling to? 2. So final minus, where are we starting? Initial. All right, so while I set this next one up, you guys go ahead and calculate. The first couple rows do the first one, and the second couple of rows do this next one. Let's get our two numbers. Go ahead. Sig figs here I'm not going to freak out about because we're at energy levels that are integers. They don't have sig figs. There's no sig figs in this problem, and you can't really use a constant, so just round to 3. It's not a big deal. For the first one, 6 point, yes, it should be negative. Good call. 6.534, so 6.53 times 10 to the what? Negative 19. Did anyone else get that? Okay. Times negative 4.5. 5 what? Times 10 to the negative 19. What about this guy? Okay. So if I were, I'm not going to actually have you do the color, but if I were to ask you the color, I would provide you with a table of some sort. I probably put color with frequency. Probably. Would be something more that I do. So if I would put color with frequency, what would you have to do? Convert it to frequency using E equals HV, right? And then you could look at the table and figure out the color. But just tell me, based on the energy, what color, which one would have a higher energy color? So this is a bigger number, right? No, wait. Don't look at the negative. So this is actually a bigger number. Remember, this just tells you direction that the packet is going, right? So this packet is bigger. So this is the higher energy right here. That being the higher energy, you would have more of your blue or violet as compared to something like this, which would be a smaller packet with lower energy. Make sense? Yes? Yeah, if the first one were negative and the second one were positive, what that's telling us is this would be the absorption of that color. This one would be the, I'm sorry, backwards. If this were negative, this would be the emission of that same color. This would be the absorption of that color. So the magnitude tells you what the color is, or the frequency or the energy. The sign tells you whether it's being absorbed or emitted. Okay? But the size of the packet is merely based on the magnitude of that number. Got it? I think that's the last slide for the day. Yeah, it is. So tomorrow you're going to learn more true chemistry about the invention of orbitals. I just want to flip through real quick and show you a couple things. We are going to be flying through the periodic table. Okay, if you haven't had chemistry in a while, you need to read the book for the first couple days of the chapter, because I am going with the assumption of knowledge that you kind of remember electron configuration. You kind of remember the orbital types, how many electrons go into an orbital, how many orbital types there are in the S and the P and the D, all that kind of stuff. So I'm moving fast. So be sure to read ahead. Yes? You mean the noble gas configuration? Yeah, I mean, but the AP will change. The AP asks for both. Sometimes the AP says noble gas accepted. Sometimes, and more often than not, they say write the full configuration. So try to review all that stuff. I'm going to kind of expect you to think about it ahead of time because today was not too bad. All right, that's it. I'm going to hand back y'all's tests, and we'll give out our high score sticker.